Hi everyone, we'll continue our talk of limits by adding infinite limits and limits at infinity. To start, let's review polynomial functions. A polynomial function can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus a sub 1 x to the power 1 plus a naught. N is an integer and it's greater than or equal to 0. A is a real number, but the first term, a sub n, can't be 0. Basically, what a polynomial function is a bunch of terms that have powers, and those powers have coefficients. When we look at the limit as x goes to positive or negative infinity of f of x, this is really determined by the leading term, which is a sub n x to the n. Let's start by looking at a graph. So here I have a graph of a polynomial function, which is a smooth curve, and I'm wanting to look at the limit as x goes to infinity of f of x. Infinity is the right side. So as I'm moving along this function, I'm saying what happens as x gets bigger and bigger, and what you see is f of x is getting smaller and smaller. So when x goes to infinity, f of x is going to negative infinity. On the left side, when x goes to negative infinity, we want to see what happens to f of x. So again, we can trace along the function and look as x is getting smaller, it's going toward negative infinity. I see my function is going back up, which says it will go to positive infinity. It's important to note that this is the first time we've talked about limits where we didn't put a number on them. Before we were saying there was a limit and that limit was going to be a number. Now we're looking at limits at infinity and infinite limits. You'll see the positive and negative infinity are used as answers. Let's try that again. Here's another function, kind of looks like a W, and we want to see what happens when x goes to infinity. So we're going to trace along this function and we can see as x goes to infinity, so does f of x. It's getting bigger and bigger. So we write positive infinity. Then when we look on the left, as we follow along x and we're going toward the negative values of x, we see that the f of x is also positive. It's going up. So we write that that is also positive infinity. The limit as x goes to infinity for a polynomial function can be found by looking at the first term of the polynomial and specifically looking at the leading coefficient. When a sub n is positive, the limit as x goes to infinity will be positive infinity. When a sub n is negative, then the limit as x goes to infinity will be negative. So this just says positives go up, negatives go down. To find the limits at negative infinity, we have the shortcut. Even powers match, odd powers are opposite. So what do I mean by that? I mean even powers match, so the limit on the right will be the same as the limit on the left. What happens at infinity will also happen at negative infinity. Odd powers are opposite, says whatever happens on the right, the left will be opposite. Let's take a look at that. Let's say I have f of x is 5x to the 7th plus 8x to the 4th minus 2x plus 100. My leading term is 5x to the 7th, and this 5 is positive. That says the limit when x goes to infinity is positive infinity. And then I'm looking at 7 being odd, and I just said odds are opposite. So what's the opposite of positive infinity? It's negative infinity. This time I have f of x is negative 3x to the 4th plus 8x cubed plus 6x. The first term, negative 3x to the 4th, is negative. So that says when I look at x going to infinity, I will get negative infinity. My power is 4. 4 is even. Evens match. So on the left side, I also have negative infinity. They're both the same. Let's try one more. Here I have f of x is negative 9x cubed plus 2x squared plus 10x plus 3. So I'm looking for the highest power. That's my negative 9x cubed. The negative 9 is my start. Because it's negative, when x goes to infinity, f of x goes to negative infinity. My power is 3. 3 is odd. Odd says opposite. So the opposite of negative infinity is positive infinity. Last one. I have f of x is 2x to the 8th plus 7x cubed plus 10x. So what do you think happens when x goes to infinity? Would it be positive infinity or negative infinity? Hopefully you're thinking positive because 2 is positive. And then let's look at 8. 8 is even. Evens match. So the limit when x goes to negative infinity is also positive infinity. Same. So rational functions basically just boil down to a ratio of two polynomials. So let's have a quick review of this idea of an asymptote. Vertical asymptotes were vertical lines, so they look like x equals a. And what happens is vertical asymptotes occur if there's some kind of value in the domain of f of x where f of x goes to either positive or negative infinity when x gets close to a. Horizontal asymptotes are horizontal lines, so they're going to be y equals b. Horizontal asymptotes occur if f of x goes to this number b as we get close to positive or negative infinity. So horizontal asymptotes become an end behavior. Vertical asymptotes are where the graph goes to positive or negative infinity. This is the graph of f of x as x over x minus 2. Can you tell where the asymptotes of the function are? Remember, vertical says, is there a place like it looks like it's going to infinity or negative infinity? And I can see right here, it looks like I have a line that runs through x equals 2, where I do go up to infinity and down to negative infinity. I also can see there's a horizontal asymptote right through here. So this is at y equals 1, because as I look to the right and as I look to the left, it looks like my graph is headed toward 1. We will write, we have a vertical asymptote at x equals 2. We have a horizontal asymptote at y equals 1. Now let's look at some limits. Let's look at the limit as x goes to 2 from the positive side of f of x. So remember, we look at 2, the positive side is on the right, and I want to see what happens as I get closer and closer to that value of 2, and my value is going up. Because it's going up, we want to say that the value is going to positive infinity. Now let's look at the value of the limit as x goes to 2 from the negative side of f of x. So I'm on the left side of 2, I'm coming towards 2, and I can see my value is going down. So that says my limit is negative infinity. Positive infinity, negative infinity, those are not the same. And more importantly, those are not numbers. So the limit as x goes to 2 does not exist. Even if these had been the same, if they were both positive or both negative, we would still say the limit as x goes to 2 doesn't exist because infinity is not a number. So remember, limits are still numbers. So if they ask for an overall limit, you would say d and e, but for the right side and the left side, we can say infinity or negative infinity. This time I have the graph of 2 over x minus 3 squared, and let's see if we can see the asymptotes. So first, do you see something where it looks like the function is headed toward infinity or a negative infinity as it gets close to a particular number? I'm hoping you said yes. It looks like as you get close to x equals 3, that the function is headed toward infinity. And then for the horizontal asymptote, we want to say, is there something where we see like a tendency? So on the right side, on the left side, does it look like there's some kind of end behavior? And I do see that there looks like there is a line really right on top of the x-axis where the function is flattening out. So we want to say the vertical asymptote happened at x equals 3, and the horizontal asymptote happened at y equals 0. Now let's talk about the limit as x goes to 3 from the positive side. When I look at 3 and I come toward 3 from the right side, I'm going to positive infinity. If I go to the left side and I travel towards 3, I also go to positive infinity. So the left side and the right side are both going up. So let's write that in. The limit as x goes to 3 from the positive side was positive infinity. The limit when x went to 3 from the negative side was also positive infinity, but the limit overall does not exist because it is not headed towards a number. A function r of x equal to p of x over q of x has a vertical asymptote at x equals a if r of x goes to positive or negative infinity as x approaches a. But to find it, here's the important part, we're going to set q of x equal to 0. So we look at a place in the denominator that's equal to 0. Let's go through and find some vertical asymptotes. So this first one, I have x squared plus 3 over x minus 3 times x plus 4. The vertical asymptotes, I look at the bottom, has x minus 3 equals 0 when x is equal to 3, x plus 4 equals 0 when x equals negative 4. So I have two vertical asymptotes, one at 3 and one at negative 4. We're going to try to find the limit as x goes to 3 from the positive side. When we start to break this down and we're looking at what's happening, we know since there's a vertical asymptote that it's either going to positive infinity or negative infinity. So I'm going to try to make this simple and think I only need to know, is this going to be positive or negative? So I want you to think about, we're putting in a number a little bit bigger than 3. So if I put in a number a little bit bigger than 3 and I square it and add 3, it's going to be positive. Then I have a number a little bit bigger than 3, and I subtract 3, it will be positive. And then that number bigger than 3, when I add 4, it's also positive. So positive, positive, positive says this goes to positive infinity. So I'm avoiding actually having to plug a number in, and I just think about what kind of sign would I get. On the left side, I'm picking a number just a little bit smaller than 3. Think like 2.9, 2.99. When I take that number, like 2.9, and I square it, and I add 3, it's still positive. But the x minus 3, think about 2.99 minus 3, that's going to be negative. The 2.99 plus 4 will be positive, but this positive, negative, positive is going to give me negative altogether. So we're just doing the sign to tell us what's happening, positive or negative. Again, we know this is not going to give us a limit at all, so here I can write d in e. Now let's look at f of x is 6x minus 1 over 8x squared minus 8. We're going to start by finding the vertical asymptote, but I'm going to rewrite it. I'm going to say this is 6 times x minus 1 over 8 times x squared minus 1. I can continue with that. I have 6x minus 1 over 8 times x plus 1, x minus 1. So factored form makes it easy for me to see the asymptotes. I'll have two vertical asymptotes. I have x is negative 1, I have x is positive 1. Now we're ready to look at some limits. The first one says find the limit as x goes to negative 1 from the positive side. It might help you to look at a number line and think about negative 1. And the positive side would be a number just a little bit bigger, maybe something like negative 0.9. So what you're thinking is you're doing a negative number times 6 minus 1. That's going to be negative. 8 is positive, so I'm just going to write a plus to represent the 8. And then this number, negative 0.9 plus 1, would be positive. But then that negative 0.9 minus 1 would be negative. I have negative, negative is positive. So this is going to positive infinity. Then I said let's look at negative 1 from the negative side. So now we're over here. Maybe like negative 1.1 would be a good number to think about. I have 6 times negative 1.1. That's negative minus 1, still negative in the numerator. On the bottom, negative 1.1, I'm going to say plus 1. That's going to be negative. I still have my 8 that was positive. And then negative 1.1 minus 1 is also negative. Negative, negative, negative says negative, so I have negative infinity. Overall, the limit does not exist. Let's look at limits at infinity. Look at the function, and let's find the limit as x goes to infinity. So we're going to follow the graph, and we're going to see as I go to the right, I'm getting closer and closer to the x-axis, which is 0. So we'll say the limit is 0. Let's look on the left side. If I look on the left and I go towards negative infinity, I'm also getting closer and closer to the x-axis, which means it's getting close to 0. A rational function r of x has a horizontal asymptote at y equals b if r of x goes to b when x goes to positive or negative infinity. We have 3 rules for finding the horizontal asymptote, which will also be the limit at infinity. We're going to start with r of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 1 x plus a naught over b sub m x to the m plus b sub m minus 1 x to the m minus 1 plus dot 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 b1 x plus b naught. R of x has a horizontal asymptote at a sub n over b sub m if n is equal to m. So when our powers for the numerator and denominator are the same, then we just take the ratio of the leading coefficients. R of x has a horizontal asymptote at y equals 0 if n is less than m. So if the power of the denominator is bigger, we have a horizontal asymptote at 0. If the numerator has a greater power than the denominator, then there will not be a horizontal asymptote. Here's our first example. F of x is 2x cubed minus 3x plus 9 over 7x cubed plus 8x squared. We only need to look at the leading term. I have 2 and 7, so my answer is 2 over 7. The rules that we have for finding the horizontal asymptote will be exactly the same as finding the limits at infinity. So given the limit as x goes to infinity of 54x minus 60 over 3x plus 15, I take the top 54 divided by the bottom 3, I simplify that to 18. The limit as x goes to infinity of 10x squared plus 5x minus 9 over 2x squared plus 8x plus 3 simplifies to 10 over 2 which is 5. Our second example says, if we have f of x is 8x plus 3 over 5x squared minus 1, and we're looking for the horizontal asymptote. Notice the power on the bottom is bigger. That means the asymptote is y equals 0. What about if we have f of x is 3x to the 4th plus 2x over 7x plus 5? The power on the top is 4, the power on the denominator is 1. The top being bigger says there's no horizontal asymptote. Let's try an application. The average cost for making x chairs is c bar of x is 35x plus 8,000 over x. Find the limit as x goes to infinity of c bar of x. When we look at it, the powers are the same, so I have my 35x on top, I have x on the bottom. 35 over 1 is 35. Let's graph the average cost function and show the horizontal asymptote so you can see this in action. So in Desmos, I'm going to graph f of x for my c bar is equal to parentheses 35x plus 8,000 divided by x. Right, notice that we don't see anything right now. It's because our values for our x and y axis aren't appropriate. One thing we could do to help a little is we could say here that x is only going to be positive. So I'm going to put in here that x is greater than 0. I'm not putting greater than or equal to because I can't divide by 0. Then I could just zoom out until I see the graph. Now I can see what's happening to the graph. The graph was decreasing and it gets smaller and smaller, but it looks like there's this stopping point. Now we said that the horizontal asymptote would be 35, so let's try that. Y equals 35, and we can see how well that lines up with the graph. Let's do one more application. The percent of a city's population that has received a vaccine X weeks after the vaccine is available can be modeled by P equals 150 x squared minus 28x minus 60 divided by 2x squared plus 8x minus 5. Let's first find the limit as x goes to infinity of p of x. What we want to do is look at the powers. The power in the numerator is x squared, power in the denominator is also x squared. The powers are equal, so we do 150 over 2, which is 75. So this says, in the long run, we won't have more than 75% of the population that received the vaccine. Part 2 says let's graph it and again show the horizontal asymptote. In Desmos, we're going to enter f of x equals parentheses 150x squared minus 28x minus 60 divided by parentheses 2x squared plus 8x minus 5. Okay. This time we can see something on the graph, but before we do anything else, I'm again going to tell it x is greater than 0. We could also do greater than or equal to. So now we see it's only in one part of the graph. Again, we could zoom out until we get a nice picture of what's happening, and I can see this nice curve. We can also put in our asymptote y equals 75, and then we can see this tendency that as time goes on, there was a big change at first about how many people were getting the vaccine, but at some point it curved over and we started to head towards our asymptote, which is our limit at infinity. That wraps up our introduction to limits. Next time we'll work on continuity.